batch-type bioreactors to the use of continuous flow reactors. His company claims that the reactor can shorten the duration of meat cultivation from several weeks to just a couple of days. Their concept seems to be very convincing, as they recently managed to not only get some sweet grants, but also funding of 1 billion million British pounds. I would now like to hear from you, Leo. What makes Cellular Revolution so convincing, and what does this company offer the world?
Yeah, thank you so much for that introduction. And I really do hope that at least a few years from now, we can also attain that 1 billion mark. It would be amazing for the company and for the industry, but let's hope and see. So let me just share my presentation. Welcome all. My name is Leo Groenewegen. I am the CEO and one of 3 co-founders of Cellular Revolution. The goal of Cellular Revolution is basically to revolutionize the way cells are grown. We are one of few B2B companies in the culture meat space, and we are actually developing enabling technologies that would allow for cultured meat B2C companies to produce their products at scale and do so much more cost efficiently as is currently done. The company is based out of Newcastle, UK, founded in late 2018, been operated since 2019, and have been steadily growing our team. I founded the business with 2 co-founders. First one of them is Professor Jay Connon, who's the CTO. We've got Martina Miotto as the CSO, and then myself, of course, as the CEO. In the past 3 years, we've grown to a team of 10 plus employees, and we're really seeing like a high growth in the industry. So what we're doing as a business, we always like to say as a company, part of our vision is that we are bio-inspired. So we basically looked at nature. We looked at current bioreactors, at cell culturing technologies. Actually, we saw that if you look at humans, at animals, cells do not grow in batches. I mean, you don't wake up tomorrow morning with 10 billion cells available to do whatever they need to do. But actually, within your body, in an animal body, every second, every minute, cells are growing, becoming what they need to become, and doing what they need to do. So we thought of that, like, if in nature, in humans, in animals, this is done basically continuously, why are we in the industry growing things in batches? So we took a hard look at that, spent several years of R&D, and actually found a way to produce cells continuously as well in a bioreactor setting. This you will see later on comes with huge gains and benefits. Generally speaking, our tech is not just applicable to the culture meat industry, but basically anybody trying to grow cells at scale could use and could benefit from our technology. So whether you're in cultured meat, cell therapists, biologics, anyone really needing large quantities of cells can benefit from a move from batch production to continuous production, as has also been done in several different industries. For example, the automotive industry, the chemical industries, many of these industries over the past decades have made the move from sort of a more batch-based or individual production system to fully optimized and continuous productions, which always have proven to be more efficient. So for the ones that don't really have a culture meat background, so what is sort of in easy terms the difference between, say, conventional meat and cultured meat? And what are sort of the key takeaways there? Well, of course, what is quite obvious is animal meat has clear environmental issues or considerations. Greenhouse gas emissions, CO2 emissions, deforestation, these are all sort of issues really, especially nowadays, attained or attributed to the production of meat. Culture meat, against that, can lower, for example, it's estimated that culture meat lowers the amount of water used to produce meat per kilo, basically by about 90%. CO2, greenhouse gas emissions, by about 80%. So it's a huge positive impact, actually, that culture meat could have on the environment. Conventional meat, of course, has its clear ethical issues, as in you need to slaughter animals to produce protein, or to produce meat products. And of course, there are both vegan, vegetarian, or plant-based options, and culture meat are clearly superior, because actually you can create this products, this meat, without harming anyone, basically. Thirdly is health concerns. meat can cause health concerns both through the consumption. But actually, also what can be the case is, for example, that your fish could contain microplastics, arsenic, or for example, your beef might be spoiled with certain types of E. coli bacteria due to sort of improper handling of the slaughter process. And these are all things, sort of all these three issues combined: environmental issues, health concerns, ethical issues, are all in a way solved together with by culture meat, together with, of course, other protein sources. Not saying culture meat is the holy grail. It also has its downsides, but clearly has some benefits as opposed to conventional meat sources. And there's also other benefits, but just don't have time to mention everything right now today. So the way actually you procure or create culture meat, sort of in a nutshell, is generally speaking, you would take an animal. In this image, I have a cow. You would basically do an aspiration of cells, which is somewhat likely to donating blood or taking a blood sample. So you would extract these initial cells from the animal, again, in this case, a cow. Then in the next stage, you would actually, for example, say you have 100 million cells collected. Then in the next stage, you would go for the cell proliferation phase. Basically, that's the phase where you go from the 100 million cells, for example, to billions and billions of cells. So really, that's why you try to create a mass. And that's exactly also where our proliferation bioreactors come in place. So after you have created all these cells, you need to create something out of it. You need to put them in the scaffold so they become texturized. So, for example, you can make a burger patty out of it, a sausage, or even a whole cut steak. So that comes after the differentiation phase. So after you decided what these cells need to become. So after you decide to make either fat cells or muscle cells, you put them into a scaffold and you create this texture. And that basically leads to your burger, sort of in a nutshell. And this is what culture meat is. The one thing, of course, which is very nice as well about culture meat is it is basically the same as conventional meat. I mean, you use cells; these cells become meat. So molecularly speaking, it is the same product, as opposed to, of course, plant-based proteins, which will remain slightly different. I mean, they can be amazing taste as well and texture, but they'll never be exactly the same, which is one of the benefits of culture meat. It can be exactly the same as meat, as conventional meat. So the culture meat industry for us is a key market, but as a business, of course, we are also active in the other industries. What is really interesting to see, which is also why I have this graph, is the potential of cultured meat as an industry, which numbers here, of course, are all projections, not necessarily correct, but it's about sort of the magnitude. So if you look on the right-hand side, sort of after 27, which is what we think is probably when cultured meat really start taking off. If you just see the potential market size of culture meat, also compared to biologics and cell therapies, this is a huge industry. At the moment, the general sort of processed meat or meat industry is several trillion of dollars, of course. Say culture meat, takes 10% of that or 1% of that, that's already billions and billions, making it one of the most lucrative nascent industries that you can probably get into at the moment. With almost basically virtually no sales right now in 22, with only culture meat being available in one place in Singapore, to within the next sort of decades, culture meat potentially being available globally through retailers like your local supermarkets, whether it's your local supermarket in the Netherlands, your Albert Heijn, or whether it might be your Carrefour in France or your Tesco in the US. It doesn't really matter. The goal is to, within sort of this coming decade, to really get culture meat to the mass consumers. And we think that is very much possible. So what is the challenge of culture meat? Why is culture meat not readily available yet? Well, there's a few reasons for that. Of course, one of them is regulatory approval processes, which in many regions of the world are slowing down, of course, culture meat market launch. But actually, there's some other issues. So the biggest challenge, or one of the biggest challenges actually, is scalability. So if you would want to feed the world with culture meat, you need to produce tremendous amount of cells. We ran the numbers a couple of months ago by now, and we came to the conclusion that you will need to produce 10 to the factor 20 cells per annum, which for most people won't really say much. What is 10 to the factor 20? It could be anything. If you put it on context, it is either all the grains of sand we have on planet Earth, or all the stars in the observable universe. And we will need to produce these every year. So it's a huge scaling issue. And that's also why there's such a huge need for more efficient technologies, whether it's better media solutions, better bioreactors, better scaffolds, better cell lines. This all needs to be improved in order to really make Cultivated a commercially viable product. For many companies growing cells, there's a few issues they're facing. Current types of bioreactors, for example, have the challenge of growing basically enough cells of the right type and doing it in the right conditions. In many cases, bioreactors are limited to surface area, especially in the case of adherent cells, where there's always a finite amount of surface area for cells to grow on and to multiply on. A lot of companies are still struggling with either with the use of serum in their products or with finding of very suitable and cost-efficient serum-free alternatives. If you look at how the Cultivated development again looks like, is going up quite rapidly here on the right. So if you look at the red line, you see the demand for Cultivated going up sort of until 2030, 2040, and so on. Actually, the capability of current technologies, if you would use currently available batch-based bioreactors, you will not be able to keep with this increase in demand. So what we need is new technologies, innovative technologies that are 3 times, 4 times, 5 times, maybe even 10 times better than what's available now. And that's the only way we can really bring full-scale, commercially available meat to the market. So what we've done, we as a business have developed a novel type of technology that allows for a switch from, again, batch-based production to continuous cell manufacturing of adherent cells. We've done so by having IP protected peptide-based coating technologies that actually allow for increased cell proliferation and also allow for a self-detachment of the cells, which is part later on of the bioreactor system. I will tell you about in a second. Generally speaking, our continuous cell manufacturing system allows for a few things. So it allows for serum-free continuous manufacturing of cells. You can fully close and automate the system, making it much more efficient and easy to use. That in turn leads to footprint reduction, resource reductions, higher yield, and tremendous cost saving on both the CapEx and the OpEx sides. So here's a quick video about the difference basically between batch and a continuous system. So in a batch system, you would seed the cells manually. Generally speaking, scientists would seed the cells on the surface. They will seed, they will grow, they will proliferate. And after that, you will normally cleave them with a chemical like trypsin, for example. You take them all out. You would clean the bioreactor. You will have downtime for a few hours. And then you would have to start this process again from scratch. So reseed them, let them grow, proliferate, clean them out, start again. So in a continuous cell culture system like we have developed, in green, that is our sort of proprietary peptide-based coating that's under it. Cells would, of course, also need to grow, proliferate, and they always release. So the benefit here, you'll see it in a second. So these cells are continuously growing, proliferating, self-detaching. All the cells you see that are releasing, they will go in our harvesting chamber and get automatically harvested. That immediately opens up a space again for a new cell to take their place. They will grow, proliferate, self-detach. That opens up a new cell, place for a new cell. They will grow, proliferate, self-detach. So there's always 24/7 ongoing cell production, cell collection, cell proliferation. And that in turn can create up to a three time-ish increase in productivity of your bioreactor system. Meaning that in a facility, for example, where you make, I'm just saying a random number now, instead of producing, say, 10,000 burgers a month. With our technology, for example, you could potentially do 30,000 a month, which will have, of course, a huge impact on your profitability, your CapEx, your OpEx, and so on. So if you look at culture meat facilities, I mean, some of you might have heard that earlier this year, for example, he just announced a culture meat plant to be built in Qatar with estimated cost of around 200 million. Other research groups have estimated costs between, up to 450 million, even for full-scale 10 kiloton production plants. And so really full-scale culture meat production plants will probably cost several hundreds of millions. Due to the fact that so much, especially using current technologies, so much technology is needed, so much bioreactors are needed in order to actually create the right amount of meat that people will be demanding. This in turn comes with some issues, of course. It comes with huge sort of capital upfront expenditure for the companies. And it means that we really need the scale to really produce sufficient amounts. For a company like us, actually, that creates opportunities. As our bioreactors, of course, are so much more efficient, we could actually have a large impact on the CapEx expenditure. So we might be able to push this, say, 240 or 450 million down by several millions of dollars, actually lowering the initial investment required by the culture meat companies, and immediately also having a positive impact on the cost of the end product. So again, our tech allows for a move from a batch to continuous cell production system. We do that by combining a patented beta-based coating that allows for continuous cell growth and detachment, together with a novel designed bioreactor. If you look here on the graph on the right-hand side, you can see that, it depends a bit on the exact batch system you're comparing it to. But generally speaking, you are about 3 times more efficient again when using a batch-based system, when using a continuous system as opposed to a conventional batch system. So the benefits here. This is sort of what I touched upon a bit earlier. You can reduce your bioreactor volumes by about 3 times, meaning that either you can, of course, fit many more bioreactors in the same facility, or again, you just use fewer and save on the cost there. So in a fully designed factory, fully designed facility, like I mentioned in the other slide, you can have tens or even hundreds of millions of savings when you really go to large-scale cell production. And that all, of course, influences the end cost of goods of the products that will be in your local supermarkets. If you combine sort of our impact on price reductions together with the impact on price reductions of newly designed scaffold and newly designed media solutions, there's really a clear feeling that in the coming years we'll really be able to put culture meat much closer to the price of conventional meat and plant-based meat sources, which is very important, of course, for future uptake of the products. Well, now I have everybody here anyway today. I'd like to know that as a company, of course, we're always looking for talented scientists, engineers, or anybody with a real passion to move into this sort of nascent, new and exciting technology-based industry where we are, for example, really working at the intersection between sort of biotech and food tech. And anybody that's here today is welcome to also later on contact me or my colleagues to see if there's any suitable roles out there. Quick update, of course, we are formerly a spin-out of Newcastle University. We were able to incorporate with the help of Newcastle University, where at that time my co-founders were employees. We've received funding both from Innovate UK, which is a UK-based government-funded institute, also the European Regional Development Fund, and have also received investments over the past few years by, for example, North Star Ventures, CPT Capital, and several other investors that really help us to become the business that we are now, to help us to grow towards a larger team, larger facilities, better science, better bioreactors, as we sort of are keeping up with the developments in the industry, and we'll be moving from sort of small scale, so like we're moving from small scale sort of, bench-based bioreactors to in the future having bioreactors that might be hundreds or thousands of liters in size, and moving along with the rest of the industry. So the support of these organizations has been highly appreciated. Thank you for listening to my presentation today. I mean, feel free to reach out to email, LinkedIn if you have any questions. And looking forward to to any questions you might have now actually in the QA session. Thank you so much.
Thank you for the presentation, Leo. So now we have the Q&A time, and I don't see yet anything, so maybe I can start asking you something. What market are you most excited about for the next few years in a global scale?
Well, I think the cultured meat industry as a whole is going to make a very big impact. Of course, the whole cell egg market in general, you can divide it in several organizations actually, or groups. I mean, you have companies working on meat as in beef products, pork products. You have companies working on leather. You have companies working on milk products. It's really a industry where a lot of things are possible, and it's really gonna make a big influence, especially for future generations, on how they consume food, how they even consume products like, for example, leather, and how they also interact sort of with both other species, other animals, and the environment.
Mm-hmm. And do you think the regulations are going to allow you in the next few years to be able to get your products out in the market, or is that something that you reckon will take a long time?
So I mean, like I showed, like back in December 2010, December of not 21. So December 2010 or November 2010, we had the first approval, of course, in Singapore of cultured meat, small scale. A lot of companies are saying that most likely the first US approval will come mid to late this year, with Europe potentially not being far behind. Initially, of course, that will be small scale, high end production. High end boutiques, one or two sort of specifically chosen restaurants. But in the years after that, there's going to be this move to full scale commercial products that you can just buy at your local retailers. That is still a few years away. But I do think that the initial regulatory approval in the US and Europe will be coming sooner rather than later. Yeah.
That's very exciting. We have some questions in the chat. So is there a specific topic or issue that your company is currently researching on?
Well, there's many different things we're working on. So we're working, generally concept, of course, we're using is moving from batch to continuous manufacturing system. And there we are investigating, of course, how that works with different cell lines, different cell types, different species, but also looking at what type of bioreactor is best, of course, how to design a bioreactor, what kind of services to use in the bioreactor. Is it better to use, flatbeds, hollow fibers, microcarriers? These are some of the things we are continuously working on to identify, something that might work on small scale, might not be the most efficient at very large scale facilities. And these are things that our engineers and our R&D scientists are always sort of working on. So look, okay, how are we going to scale things up? What are we going to need in the future? And how's it going to look like?
Okay, thank you. Then we have other questions. Someone is wondering if your peptides are cell type specific, or if any cell type can proliferate on the peptides that are used.
Yeah, so the idea is that our peptide-based coating and the bioreactor basically could work species and cell agnostic. At the moment, all our tech is sort of optimized for adherent cells. In the future, we might make bioreactors that also work very well with suspension cells. But generally speaking, they should work whether you have specific types of fish cells or beef. That should not be a real difference in efficiency, and it should work no matter what.
Okay, thank you. We have another one. Do you think that this food will be accepted differently from different kind of consumers? And how do you think you should approach the problem to improve its acceptability?
Yeah, so consumer acceptance will depend per per customer segment. It will depend per country, but also per consumers. I mean, it is most likely that sort of the younger generations will take up on culture meat faster than, for example, people that are already in the 70s or in their 80s. There's people that living in cities maybe might be more willing as opposed to people on the countryside. There's so many different variables actually on which consumers are more likely to purchase cultured meat. And there's been quite some studies by now on consumer acceptance in general of cultured meat, also looking at differences between companies and specific sort of demographics. But I do believe that we should start with, well, in a way, I mean, you try to get the products to everyone. Most likely, sort of the younger generations will be the ones actually sort of leading this change, because they will see what is going wrong. They will see what they need to do for their future and the future of their children, for example. And that is where you can probably make the most impact as well.
Great answer. So I don't see any more questions right now. So maybe we could take a break before the next session. Oh, I see another one now, right now. When doing research and process optimization, on what volume scale do your reactor works?
Yeah, so we are building different scales of bioreactor, depending on the needs of our potential customers, basically. So at the moment, like I said, we are at sort of bench scales. So it's just a few liters in size. This will be upgrading to tens of liters and later on to hundreds and thousands in the sort of longer future. So now it's just a few liter, but say within a year, it will be much larger already because we're really scaling it up really quickly.
Mm-hmm. And how long does it take you to finish a product from starting off the batch to finish?
That depends on the cells that are used. Some cells grow faster than others, depending on the doubling times, the nutrients, and so on. So that's not something we can actually influence that much. It's more cell specific and depends on the cells that, for example, our customer is using and supplying to us.
Okay, thank you. So I guess now we can take a small break. There is a question from Subrat. You can open your mic if you are not able to use the chat.
Yeah, sorry, I'm not able to use the chat, but I do have a question. Is there any chance that in the future you can make any other kind of meat, for example, chicken, like because you're focusing on beef meat right now?
So we are not specifically focusing on one type of meat. Like I said a few minutes ago, is you can use basically any type of species or cells with our bioreactor units. So whether it's beef or pork cells, or whether it's some kind of fish cells, it's all possible in our bioreactor.
And you just change the media settings accordingly. Do
Yeah,
you need this?
Yeah.
Yeah. Okay. Thank you.
There is something else. So are there main differences between cultivated meat and the medical application of cultivated cells? Or can you interchange the bioreactors?
So you can, that's the good thing for us, you can use the same type of bioreactors. You just need to optimize, of course, the media. The media solutions need to be different because you have different cells. But generally speaking, we would not need to change the design of our bioreactor. If we say we want to move from cultured meat to selling the bioreactor to a cell therapy company, then that's not needed. So that is very, very useful for us. So we can easily switch between industries and customers.
Thank you. We have another guest with its hand raised. You can open your mic for a second.
Hello. I have a question about antibiotics. At the moment, we are using a lot of them in agriculture. How difficult will it be from a hygiene point of view to, let's say, don't use antibiotics in the future for cell culture?
So it is the understanding that for cell culturing, for sure, you need far, far less antibiotics as compared to conventional, say, factory farm meat production. I don't have the numbers in front of me, I'm sorry. But I can tell you that the research that I've read is that culture meat needs far, far less antibiotics because everything is done in a much cleaner environment in a way. Because they're within this sort of almost sterile sort of bioreactor environment. Where as opposed to conventional farming, you have thousands of sheep or pigs living so close to each other, often being too close in sort of semi-dirty environments. there's much more need for antibiotics, and in the bioreactor systems, which are much cleaner, and there's no wastage and some other things around, you will need far less antibiotics. But again, I don't have the numbers here.
Thank you. So let's wait to see if we have any other question. Doesn't appear so far. Maybe I can ask you something else once again. Do you have a lot of side products and waste streams that you need to manage? And if so, how do you take care of that?
Well, not so much actually. There's some waste within the bioreactor. There's of course media. After a while, of course, the media, the nutrients are out of the media. You need to reuse / recycle some of that media where possible. And in the end, you need to discard some of that. So there's wastage. But if you compare it to wastage on a farm, it is negligent, basically. Again, the numbers will depend on the type of system you're using, the type of cells. But it will mainly come in the form of sort of used up media, and maybe in some cases also some cells that are, for example, not viable anymore, and that need to be discarded.
Got it. Thank you. We have another one. How long does your coating last? And if you can disclose, so how do you produce it?
Yeah, so it's a peptide-based coating, which is chemically defined without any traces of, for example, animal products or things. So what we have tested, I mean, I can say that we've tested it for quite amount of time. So the idea is basically that you can leave this in your bioreactor for several months before you need to replace the coating, which is quite good. It depends a bit, of course, on your cell type and the media you're running. But the coating itself is very dense, have a very slow substrate degradation, meaning that you can let cells grow on the same spot for several months at a time.
Okay, thank you. We have someone else with their hand raised. You can open your mic for a quick sec.
Hi, if I got right, the cells are they detached from the surface. Is it right? With the process, I was wondering how this affect the cell behavior during the process. If they survive because they need to be attached to the surface, how do you measure it?
Yeah, so there's basically, which is quite nice, is so once, I mean, the cell is growing on the surface. It could be, a flat plate, could be microcarriers, could be any kind of surface. And that surface is coated with the peptide coating. Basically, which is kind of the niceness of also our IP part of the story, is the moment the cell is sort of fully proliferated, there's basically a sequence between the coating and the cell that is signaling it to self-detach from the coating. Then it will self-detach, and then it will go automatically through a specific flow that we have into our harvesting chamber, and then can be further processed. Okay. So that doesn't have any negative influence on the cell or cell viability and so on.
Okay, thank you. We have run out of time right now for questions, but I will ask you to ask any further questions on our email, and we will redirect them to a podcast in which we will have our guests in the future. We are taking a 10 minutes break right now, and we will be back at 2020.
So I hope everybody's slowly coming back from their break. I would like to wait for the next speaker. Thank you very much. It is a pleasure to introduce our second speaker, Erik Martens. Just a couple of years back, in 2017, he finished his master's in material sciences at the University of Tartu in Estonia. Apparently, he was pretty much in a hurry to found his own company, which he did together with his colleagues in 2016. Since 2020, he is CEO of Gelotex, which is based in Tallinn, Estonia. Their idea is to develop scaffolding materials to produce fiber structures. The company has ongoing projects with 8 out of 10 biggest cultured meat producers worldwide. Furthermore, Gelotex offers cost-efficient solutions for the medical, textile, filtration, and energy industry. Just last year, they managed to receive 1.2 million euros in seed funding. So, dear Erik, please tell us, what is Gelotex, what are you doing, and where do you want to go?
Hello, everybody. Thanks for inviting. And yeah, happy to share more what we're doing at Gelotex and how actually we can make as a community make a cultural media reality within this decade easily. I'll pull up quickly my presentation, but it's rather focused on our product for cultured meat. But because we have some time, I'll give also a background of Gelotex. So Gelotex was founded with a different focus as we're doing today. The initial idea was to develop and produce a leather-like textile made from gelatin nanofibers. And the idea was really well received. We got some words in the beginning, and then got really good validation that this idea is worth pursuing. But that was just an idea. We actually didn't have a clear pathway towards product, but one of the things we knew right from the beginning was that in order to make this product a reality, we need to find a better way how to produce nanofibers, because nanofibers, those who don't know, are these high performance materials mostly used in scientific purposes, but also in small amounts in cell culture, medicine, also in filtration. And when I talk about scalable nanofibers, then the biggest challenge is how we can make cost-effective nanofibers out of bio-based raw materials, edible materials, for example. And we were working with gelatin, which is it's animal-based protein. And we looked around and saw that there are no technologies available, and there exists no technology to produce nanofibers on large scale. And then we set out with the goal to develop our own. We were successful. Around 3 years ago, we found a completely unique way, completely novel approach that nobody, for some reason, hadn't thought about. And then we basically solved the scalable nanofiber production issue. And a few years into the past, we made great progress with the product, but then we started to see we discovered cultured meat industry and started to also see that actually our nanofibers could by themselves might make much bigger impact in the field of cultured meat, medicine, and tissue engineering, but mainly cultured meat. And this is when we, around 1.5 years ago, we pivoted the company, having the technological background, having the IP filed regarding the, let's say, method and device, how to produce these materials on large scale, and started developing product for cultured meat. which because of our experience, we were really experienced on converting different raw materials into nanofibers. And now cultured meat industry is essentially industrial tissue engineering, and for that we need industrial technologies, industrial materials, or materials that are available on the industrial scale. And we saw that, yeah, our technology fits perfectly into that. And because of our experience or past regarding making more sustainable products, developing more sustainable technologies, it fell really well into our mission as well, making an impact in the world. And for cultured meat, I mean, Leo in the previous presentation described the technology really well, and also I think he mentioned scaffolds at some point. So the scaffolds they're to mimic extracellular matrix, basically giving a structure to the final product. Our product, if we go a little bit deeper, is a edible plant-based material that that basically helps to create a tissue, and this is essential when you want to mimic a animal-based muscle tissue or meat. Here we have mentioned our let's say initial product is a corn-based made from corn-based protein, which is Zyme. It's edible, 100% vegan, and it acts as a great scaffold. I'll talk a little bit later on that. So what are the main characteristics that are important to make a cultured meat reality? Leo also mentioned scalability. This is exactly what we are targeting with our technology, what we have solved, how to make tissue engineering on an industrial scale. Besides, let's say, scalability, our biggest benefits are unique 3D morphology, which I'll explain a little bit later, ability to make cultured meat steaks out of multiple different species, different cell lines, providing stable quality, and what's most importantly, lower costs. Because if let's say the ways how to manufacture cells on an industrial scale and tissues is really expensive, because this is why it has never been done before. And mainly, yeah, it's the technologies that prevent that to happen. And our technology enables us to reduce the cost of nanofibers more than 90% ultimately on scale. So how it works is that basically you and now I can refer back to Leo, you take the cells from the Leo's bioreactor, for example, and then these cells are just floating around. It's a completely unstructured mass. It's nothing like a meat, and scaffold is needed to provide a structure for the end product. And our nanofibers mimic the extracellular matrix. Mimic the extracellular matrix as best as it is possible, creating a suitable environment for the cells to grow into tissue. So on the left, you can see a SEM pictures electron microscope image of a extracellular matrix, which is basically a stuff that holds the cells together to make up a tissue. And to make a artificial tissue outside of a host environment, host body, you need to mimic that structure, and our nanofibers do really good job on that, especially to one of the competing and one of the other ways how to make nanofibers, electrospun nanofibers, which are very planar and quite expensive. So this is another, let's say, a added benefit of our materials, is this unique structure, besides delivering the lower prices as well. Here on the picture, it's quite blurry image, but you can see these lighter green lines, which are elongated cells, and these have differentiated already. So the cells that are, imagine the cells that are floating around in a solution, and when they find our material, they feel like, okay, yeah, this is like it's a familiar place for me, and they start to differentiate into muscle tissue. And this is exactly what nanofibers are good at, but the main challenge has been the scalability, so that we have solved that. The material, regarding the current status of our company, so we're piloting with a lot of cultured meat companies who are developing their own either bioreactors, growth media, scaling up their production on some scale. So yeah, they now have also our material on their table to integrate with their production, and this is exactly what our main, let's say, commercial milestones are. The material itself, like I said, can be made out of a lot of different raw materials, because this is we are not married to just one raw material. We can convert a lot of different polymers, plant-based edible polymers, into nanofibers. Few examples of other bio-based polymers are, for example, soy protein that we're working with, that we also are working towards. Then there are pea proteins, which is also a really cost-effective material. And how when after you plant the cells on it, they start to form their own ECM and also eat the scaffold on the same time. So ultimately, our material gets eaten and the muscle tissue is formed. So that's basically how it works. Yeah. These are few, just let's say, advantages of our materials if we look at other scaffolds on the market as well. Most importantly, the biggest challenge has been that these high performance materials that are required for tissue engineering have not been accessible, and this is exactly what we have solved. We quite recently, in the end of last year, we closed our first investment round. We're expanding the team. We're now at our new facilities. If we talk about scale, we are producing, where we have capability of producing hundreds of kilograms of material per month. But this is not, let's say, the rest of the industry is still not there yet. So we're kind of patiently waiting, but at the same time, it gives us a opportunity to further optimize our material for better performance, better yield, lower costs, and so on. So we would be ready when these billion-dollar factories will be built. Yeah. But yeah, that's pretty much it from my side. I'm happy to answer all your questions you might have. And yeah, the presentation itself was a little bit shorter, so we have some more time, longer time for Q&A. Thanks.
Thank you for your presentation. I see that people might need a couple of minutes to think up for a couple of questions, so I can start probably. In terms of both of your product and like original aspects of the worldwide market, what are you most excited for the next few years?
Definitely solving. And this is kind of married into our philosophy that the cultured meat problem is a hard problem to solve, and it won't be solved by just one company. Companies need to work together in order to make cultured meat reality happen, and this is exactly where enabling technologies such as Cellular and Cellular Revolution come in. And what I'm most excited about is the scale up, because this is one of the let's say biggest next milestones that needs to happen to demonstrate sustainable industrial scale cultured meat production. And this is actually what I'm most excited for, because really, the signs are out there that this will happen ultimately. Yeah, this is what I'm most excited for. I'm also seeing more and more interest towards not just adding some cells to your plant-based product, but really making a genuine cell-based meat product with minimal plant-based content that would, taste, feel, and most importantly, have a nutritional consistency of a animal-based meat made with cellular, let's say, cell-based technologies. So this is exactly where our materials come in to really solve the identical cell-based meat product problem. Yeah.
Thank you for your insights. We have someone with their hand raised, so you can open your mic for a sec and ask your question.
Yeah, hi, can you hear me?
Yeah.
Okay, yeah, super nice presentation and really nice technology. I was wondering, does the origin of the scaffold influence the taste of the end product, or why? Yeah, you were talking about using pea protein or soy protein, whereas the mice actually works already quite fine, as I understood.
Yeah, let's say, great question. Definitely it affects a little bit, but on which extent we still don't know, because let's say there needs to be these tests where you really make the whole process on a certain scale to find that out, because what, like I mentioned in the presentation as well, that what happens when you plant the cells into the material, the cells, first cover the material and then migrate into the material, ultimately becoming like this homogeneous structure where you have, let's say, 90% of the cells and 10% of the scaffold. And with what happens with our material is that because it's such a familiar environment for the cells start to form their own tissue, creating a muscle tissue or adipose tissue. And they start to also eat our scaffold. And so it provides like a nutritional element for the cells, and at the same time the structure as well. So our material will be degraded to some extent, and the extent of how much it will be degraded depends a lot on the process, the overall process. So different cultured meat companies have different processes. The length of the maturation phase, which is responsible of creating a tissue, takes in some cases week, in some cases 2 weeks. Heavily depends on that, how much residues will remain in the final product. Yeah.
Okay, clear. Thanks.
Thank you for your answer. From the chat, we have, is your scaffolding nutritionally relevant in the final cultivated meat product? And if so, in which percentage and which micronutrients does it provide?
Yeah, partially answered in the last question. So heavily depends on the process, of course, because our materials are made from mainly from proteins. So they do provide additional nutritional value to the end product as well. But like I said, to some extent, the material gets degraded, and this is normal. This is expected. This is exactly what we want. We want to mimic the process that naturally happens in a mammalian tissue, and then this is exactly normal. One of the interesting, we're working with other polymers as well, not only proteins, but polysaccharides as well. So this is actually something that could benefit to even advanced, let's say, cellular meat, ultimately providing maybe a fiber content to the end product, which we don't see that much in animal-based products. So, and this is actually my assumption that ultimately the, let's say, with cellular technologies, we are able to engineer even a better meat, but it takes time to get there because mostly it's about customer acceptance, and this takes time, especially accepting that yes, this can be done. Animal-based meat can be obtained from a different source. This takes time, and then when this is achieved, then we can talk about let's say even advanced, even more advanced foods. Yeah.
That sounds very exciting. We have someone with their hand raised in the chat. You can open up your mic for a quick sec.
Hi, I was wondering if there is a solution for culturing the cells on nanofibers in large scale, like a bioreactor or something specially designed for this purpose, or if you are working on this, do you have some ideas to share?
Yeah, So the scaffolds are used in a bioreactor. They can be used, our materials actually can be used in 2 different stages. We're mainly focusing on maturation phase, which is, you take the cells, put it into a scaffold, let the whole thing to mature into a tissue. But our materials also provide a really, you can make really great microcarriers out of it. And microcarriers are mainly used in a tank phase, in a proliferation phase. Which is also in, so basically the materials are used in inside the bioreactor. Yeah.
Okay, thank you. From the chat, what are the major challenges in the field of scaffold development for the meat production industry, and how could you imagine the research in the field?
The main challenges in scaffolding were like before Cellular, I would say the industrial scale nanofibers were basically you couldn't do it. There were no technologies available. We solved the problem with scalable nanofibers. There are, however, other scaffolding technologies as well. I didn't just go into that, like hydrogel-based 3D printing. Also, let's say these can be considered as a scaffolding technologies as well. But what we have seen is that when we look at the best way how to make a cell-based meat on an industrial scale, then the materials that come on a roll makes the most sense. Because these can be automized the most easily. They don't require any, let's say, compared to 3D printing, which you really need to print it. The nozzle needs to move and place every piece of scaffold in its right place, so it's not scalable. Therefore, the scalability, I would say, is the biggest challenge. In our case, was the biggest challenge, but then the next step would be the chemistry optimization. So basically, or composition optimization. We are using mainly Zyne. Zyne is a great raw material, one of the best out there. It's edible, it's readily insoluble in water, which is really important for the scaffolding materials, so they wouldn't dissolve before cells attach to them. But there are also other materials to look at, which we are actually working on right now. And the final solution might be even a blend of different polymers, biopolymers, not only a single polymer. So I would say optimization of a composition is the, let's say, the main thing that we are actually focusing on.
Thank you. We have another one. You mentioned mammalian tissues. Could this process also be implemented for other types, such as fish tissues?
Yes, it can. We have multiple pilots going on with fish cultured meat companies as well. So definitely, it's not limited to a species, and not limited even to a tissue type, let's say. So even like we have mainly talked about muscle tissue, but adipose tissue is fat tissue is really important factor in the meat. Actually, our materials in other industries have been tested also for helping the bone, let's say, tissue to reform, for example, dental applications. So scaffolding is let's say, a universal, let's say, a component in when you want to create a tissue outside of a host environment, culture cells outside of a host environment. This is what's needed. Basically, you need 3 components to make a successful cultured meat or any other cultured tissue product. You need a right cell lines, you need a bioreactor. Actually, you need one more thing. You need media, growth media, and you need scaffold. If you have these 4 in place, then you have a nice cultured product.
Thank you. We have someone with their hand raised in the chat, so can you open up your mic?
Yes, thank you for the presentation. I had a question, and also you just mentioned that your scaffolding also helps skeletal tissue to develop, something like that. I was wondering if your scaffold can help